All right, in chapter 5, we're going to talk about uniform circular motion, and we're also going to talk about gravity, right? Because gravity, in terms of the solar system, leads to what is, for the most part, uniform circular motion. So we're going to stick it in with here. And what do we mean by circular motion? And it seems straightforward, right? Circular motion means going in a circle. Right? It doesn't mean spinning in place, although it does sort of mean spinning in place too. But it means going in a circle. Well, if we rotate through an angle, as we show here, we're going to rotate through this angle. We're calling it delta theta, right? Going to rotate through that angle. That corresponds to a length of arc out here, right? I mean, that's the length of this piece of the circle is somehow proportional to delta theta. Well, it turns out the length of that out there is just the radius times delta theta. Or, if you know the length out there, delta theta is that length divided by the radius. All right? So pretty simple relationship here. The arc length, the length from A to B along this circle, is just the radius of the circle times the angle that we've gone through there. So next time you have a pizza, you can measure from the center of the pizza out to the edge, and you can calculate based on how many slices there are and dividing that into 360, you can calculate what the outer length here is on your slice of pizza. So when we think in terms of rotation angle, we also often think in terms of 360 degrees. However, when you use this formula here, right, we're talking about radians, and we know 2 pi radians equals 360 degrees. So you want your angle in radians, you take your radius in meters, and you get the radius times the angle gives you the arc length out here in meters. Now we want to start talking about, well, what does velocity mean in this context? I'm going around a circle and I'm going around and I'm going around. So what is my velocity? Well, we talk about an angular velocity as the change in angle over time. Just like we talk about linear velocity as change in position, delta x, right? If we're talking about linear velocity, we talk about delta x over time. Well, here we're talking about angular velocity. So angular velocity is delta theta over time, and this little symbol right here, right, that is a Greek letter omega. Well, Greek letter omega, a lowercase omega. An uppercase omega looks like this, like an upside down horseshoe, right? This is a lowercase omega. So angular velocity, delta theta over delta t, that is radians per second, are just a per second, since a radian really isn't a unit, right? 2 pi radians is just our way of saying we're talking about an angle, but it's not really a unit per se. Now if we want to convert this to linear velocity, delta s over delta t, well, delta s is r delta theta. So in terms of linear velocity, what's our linear velocity around this circle, right? That ends up being omega r. So now we have this set of equations, these two equations that really just one rearrange. V, our linear velocity, or the tangential velocity you're going at the edge of a circle, is your angular velocity times the radius, or the angular velocity is your tangential velocity divided by the radius. All right. So linear velocity is your instantaneous speed at any point as you move around in a circle. Angular velocity is the rotational velocity as you go around. Your linear velocity as you go around in a circle has exactly the same magnitude. All right? Has exactly the same magnitude. It's the same length all the time. No matter where you are around the circle, right? It's the same length, has the same magnitude, but it points in different directions. Right? This is the first time we've hit an instance where we're going to get in the next segment on this, we're going to talk about acceleration, right? There must be acceleration here. Why? Because the velocity is changing. And we know that for the velocity to change, there has to be acceleration, because acceleration is change in velocity over time. Now, the magnitude's not changing, right? The magnitude of the velocity is not changing, but the velocity is changing because look, here it's pointing that way, yet here it's pointing that way. And over here it's pointing over here, and here it's pointing there, right? All around this circle of this, it's pointing off in different directions. That means the velocity is changing. That means there's acceleration. And we will talk about that acceleration, that what we call centripetal acceleration, in the next segment.